Late summer 1666. A 23-year-old sits in the orchard at Woolsthorpe Manor, 60 miles northwest of Cambridge. The university closed, the plague burning through England, 100,000 dead in 18 months. Isaac Newton returns to his mother's farm in Lincolnshire, the stone house where he was born on Christmas Day, 1642, 3 months after his father died. The boy who could fit inside a quart mug died. Born so premature, his mother said he wouldn't survive the week. Now a Cambridge graduate with a bachelor's degree and nowhere to go. 2 years stretch ahead, forced isolation, no lectures, no library access, just him, his notebooks, and the questions burning holes in his mind. You think genius happens in a flash, one apple, one moment, everything solved. That's the legend. Here's what actually happened. Newton brings books, Descartes, geometry and Latin. Wallis on infinite series, Oughtred's mathematics. He brings prisms purchased at Stourbridge Fair, a furnace for chemical experiments, measuring tools, paper, so much paper. In his room upstairs at Woolsthorpe, he drills a hole in the wooden shutters, one thin pencil of sunlight. 22 feet from window to far wall, he's about to shatter something everyone believes about light. If you value documented science history like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual, using sources from the Newton Project at Cambridge University Library, which holds manuscript Ad 3958 containing Newton's actual mathematical notebooks from 1666, and from William Stukeley's 1752 memoirs of Sir Isaac Newton's life, based on conversations with Newton himself in 1726, published by the Royal Society. Now, back to the information. The world thinks color comes from prisms. White light enters glass. Glass corrupts it, color emerges. Robert Hooke says it in 1665 in Micrographia. Descartes said it. Everyone says it. Red is white light with least darkness added. Blue is almost black. The prism modifies light, creates color. Newton watches the beam. The spectrum on the wall stretches oblong. Should be circular if simple refraction. 5 inches wide, 20 inches long. Red at one end, blue at the other, Y oblong. He tests hypotheses. Maybe the glass is uneven. Maybe the angle matters. Maybe thickness. He eliminates suspicions systematically, each one crossed off. Then he tries something nobody tried. He puts a board with a slit 12 feet away, isolates one color, just red, sends it through a second prism. The red stays red, doesn't change, doesn't split further, just bends at the same angle and continues as red. He tries blue. Blue stays blue. Every color maintains its identity through the second prism. The glass isn't creating color. The glass is separating color. White light already contains every color. The prism acts like a knife, cutting white light into its components. Colors are original and innate properties of light itself, not modifications, not corruptions. Inherent. He calls it his experimentum crucis, his crucial experiment. Spring 1666, one shaft of sunlight, 2 prisms, one discovery that overturns 1,500 years of wrong theory. But the prism work is just mornings. Afternoons he's calculating. The notebooks show dates. May 20th, 1665. Method of tangents. November 13th, 1665. Discourse on fluxions. October 1666. A 29-page tract. Nearly 10,000 words. He's inventing calculus and doesn't even call it that yet. Calls it the method of fluxions and fluents, flowing quantities, how things change over time, the mathematics of motion. He needs it because the old geometry can't handle curves and speeds and acceleration, can't handle things that change. Euclid gives you fixed shapes. Newton needs fluid motion. The tract survives. Cambridge University Library. Manuscript Ad 3958, folio 48, verso through 63 verso. You can see his handwriting, the diagrams, bodies moving in circles, chords drawn from moving bodies to points on circumference, velocity relationships, and up. If a body moves towards center, velocity to each point equals the chord length, compound motion, angular motion, parallel motion, mixed motion, every motion broken into components, 7 propositions, 15 pages of dense mathematics, differentiation emerging, integration forming, the foundation appearing. By late 1666, he's the leading mathematician in the world. He's 23 years old. Nobody knows it yet. Plague year, isolation gives him something Cambridge never could. Time. Uninterrupted time. No required curriculum. No lectures to attend. No examinations. No social obligations. At Cambridge, everything's Aristotle. Ancient authorities. Fixed doctrines. Here at Woolsthorpe, he reads who he wants, thinks what he wants, tests what he wants, works when he wants. He later writes that these years were the prime of his age for invention. He minded mathematics and philosophy more than any time since, the annus mirabilis, the miracle year. Except it's not one miraculous day. It's months. Grinding, methodical, obsessive months. Problem after problem. Calculation after calculation. Experiment after experiment. Building, constructing, eliminating errors. The apple happens. Sometime late summer, 1666. We know this from one source, 60 years later. April 15th, 1726. Newton is 83 years old. His friend William Stukely visits his lodgings in Kensington. They have dinner. The weather is warm. They walk into the garden and drink tea under apple trees. Just the two of them. Newton tells him he was in the same situation when the notion of gravitation came into his mind, occasioned by the fall of an apple. As he sat in contemplative mood, why should that apple always descend perpendicularly to the ground? Why not sideways or upwards, but constantly toward Earth's center? Assuredly, the reason is that Earth draws it. There must be a drawing power in matter. That's it. That's the earliest reliable account. Stukely writes it down, publishes it in 1752. No apple hits Newton's head. That version comes from Isaac Disraeli in 1791, who invents it completely. Newton just sees an apple fall. Probably falls 100 times that summer. This time he's thinking about the moon, asking the right question. The apple falls down. The moon doesn't. Why? What holds the moon? Newton already knows about Kepler's laws. Planets sweep equal areas in equal times. Orbital periods squared proportional to distances cubed. He knows about circular motion from studying Huygens. He knows that objects moving in circles need constant inward force or they fly off tangent. The moon travels in orbit, doesn't fly away. Something pulls it. Could the same force pulling apples also pull the moon? Time to calculate. He knows Earth's radius, about 4,000 miles. The moon orbits at 60 Earth radii distance. If gravity diminishes with distance squared, inverse square law, then gravity at moon's distance should be 1 over 60 squared. 1/3600th of surface gravity. Surface gravity accelerates falling objects at 9.8 meters per second squared. Divided by 3600 equals 0.0027 meters per second squared. That's how fast the moon should fall toward Earth if gravity reaches that far. But does it? Does the moon actually fall at that rate? Newton calculates the moon's acceleration from observation. The moon completes one orbit in 27.3 days. Orbital radius 384,000 kilometers. He can compute centripetal acceleration, the rate at which the moon curves toward Earth while traveling forward. The calculation gives 0.0027 meters per second squared, exactly what the inverse square law predicts. The numbers match. The force pulling apples and the force holding the moon are the same force. Gravity extends to the moon, probably to all planetary orbits. Universal gravitation, one force, same rule, everywhere. Except his first calculation doesn't quite work. He uses an inaccurate value for Earth's radius. Gets the moon's orbital time wrong by 16%. Close, but not close enough to be certain. So he sets it aside. The idea stays alive. The calculation incomplete. He needs better measurements of Earth's size. By 1680, das Passens, new data arrives. Jean Piccard measures Earth's radius more precisely. Newton recalculates, gets within 1.6%. Now it works. Now he's certain. But that's 14 years later. In 1666, he has the insight. The method, the beginning, not the proof, not yet. People want the story to be one brilliant afternoon, one apple, one insight, everything solved. The historical record shows something else, shows grinding work, show incremental progress, shows a man who keeps subject constantly before him, who waits till first dawnings open slowly by little and little into full and clear light. He writes this himself years later. How he discovered universal gravitation. By thinking on it continually, not inspiration, perspiration, mental endurance, the ability to hold a problem in mind for months, for years, for decades, never letting go, always circling back, always testing, always refining. Look at what he actually accomplishes during these 2 plague years. By late 1666, the list is staggering. He develops the binomial theorem, states and proves it, shows how to approximate series, discovers the method of tangents, works out direct method of fluxions in May 1665, develops inverse method of fluxions, integration, by May 1666, completes 3 papers on fluxions by October 1666, discovers that white light is composite, proves it with experimentum crucis, works out theory of colors from prism experiments, begins thinking about gravity extending to moon's orbit, develops the mathematical theory of uniform circular motion. Notes the relationship between inverse square force and Kepler's third law, calculates, roughly, that Moon's centripetal acceleration matches predicted gravitational acceleration, lays groundwork for what becomes the Principia 20 years later. The binomial work starts from reading John Wallis, Arithmetica Infinitorum, published 1655. Wallis shows patterns. Newton sees further. The binomial theorem for positive integers is old, known for centuries. Newton generalizes it, makes it work for any real exponent, negative numbers, fractions. The formula becomes 1 plus x to the power n equals 1 plus n times x plus n times n minus 1 over 2 factorial times x squared plus n times n minus 1 times n minus 2 over 3 factorial times x cubed onward infinitely. Valid for any rational value of n. With this, he can find infinite series for algebraic functions. 1 plus x to negative 1 becomes 1 minus x plus x, squared minus x, cubed plus x to the fourth minus x to the fifth, continuing forever. 1 over square root of 1 minus x squared becomes 1 plus 1 half x squared plus 1 times 3 over 2 times 4x to the fourth plus 1 times 3 times 5 over 2 times 4 times 6 x to the sixth, extending infinitely. He uses this to calculate pi, starts investigating areas under curves. The curve 1 minus x squared to the power n over 2 from 0 to x, easy when n is even. Newton interpolates for odd values, guesses patterns, tests them, they work. He realizes the same answers emerge from expressing 1 minus x squared to the n over 2 as infinite series. By plugging in x equals 1 tas, he obtains infinite sum for pi over 4. Important finding. He improves it. Eventually calculates first 15 digits of pi, 15 accurate digits. By hand, using series he derived himself, from patterns he observed, from methods he invented. He's 23 years old. The optical work goes beyond prisms. He experiments on himself, takes a bodkin, large blunt needle used for drawing ribbon through fabric. Writes in his notebook circa 1665, I took a bodkin and put it betwixt my eye and the bone as near to the back side of my eye as I could, not pressing on the front of the eyeball, behind it, between eye and eye socket. Pressing forward to make curvature in his eye, there appeared several white dark and colored circles, plainest when he continued to rub his eye with the point of the bodkin. If he held eye and bodkin still while pressing, circles would grow faint and often disappear until renewed by moving eye or bodkin. If experiment done in light room so some light got through closed eyelids, there appeared great broad bluish dark circle outmost. Within that another light spot. Within that spot another blue spot, especially if pressed hard with small pointed bodkin. Outmost appeared verge of light. He's investigating how eye perceives color, whether colors are properties of light or properties of seeing. Testing. If physical distortion changes color perception, documenting everything, drawing diagrams, recording observations. Precisely. In dark room, different colors appear, reddish light, darkish blue. The patterns change with pressure and movement. He concludes colors have intrinsic relationship to light itself, not just perception. The bodkin experiment terrifies modern readers. Seems insane, dangerous beyond comprehension. But Newton doesn't see danger, sees question, needs answer, performs experiment, records results, moves forward. This is his approach to everything. No question too fundamental, no method too extreme if it produces knowledge, no observation too small if it reveals pattern. The mathematical work builds systematically. Early 1665, he finds method for approximating series, discovers rule for reducing any power of any binomial to such series. The binomial theorem, same year in May, finds method of tangents developed by Gregory and Slusius. November has direct method of fluxions, differentiation. Next year, January, theory of colors. May following, inverse method of fluxions. Integration. Same year begins thinking gravity extends to Moon's orbit. Compares force needed to keep Moon in orbit with force of gravity at Earth's surface. Finds them answer pretty nearly. All this in 2 plague years, 1665 and 1666. He writes this himself decades later, adds explanation. In those days, I was in prime of my age for invention, minded mathematics and philosophy more than any time since. The progression is visible in manuscripts. Dated entries show development. May 20th, 1665. November 13th, 1665. October 1666. Each step documented, each advance recorded. Not sudden inspiration. Accumulated work, layer by layer, problem by problem, method by method. He's building toolkit, creating machinery for solving problems that don't yet exist, developing language for describing nature mathematically, finding ways to calculate change, to measure motion, to quantify force, to predict orbits, to understand light, to explain colors, to compute areas, to determine tangents, to solve equations nobody else can solve because nobody else has these tools. This is not one man's lucky year. This is one man's capacity, the ability to sustain deep focus, to question assumptions everyone accepts, to design experiments that answer fundamental questions, to develop new mathematics because existing mathematics can't solve the problems he faces, to connect observations across domains, light, motion, mathematics, astronomy, gravity, all connected in his mind, all pieces of one coherent system. He doesn't know yet that he's building the foundation of modern physics. He's just solving problems, following curiosity, testing ideas, keeping records. The binomial theorem connects to calculus development. He needs series expansions to integrate functions. Standard geometry handles simple curves, circles, ellipses, parabolas, but complex curves require new methods. Newton expands functions as infinite series, then integrates term by term. The binomial formula gives him access to algebraic functions, functions that satisfy polynomial equations. He can now find areas under curves nobody could calculate before, find tangent lines to curves nobody could analyze before, solve equations nobody else has tools to approach. The method transforms mathematics, makes calculable what was incalculable, makes solvable what was unsolvable. His notebooks contain the evidence. Waste book shows early experiments. College notebook shows development. The October tract shows mature method, all dated, all documented, all proof of what he accomplished versus what legend claims. Modern historians analyze these documents, compare Newton's later recollections with contemporary evidence. Some dates don't match perfectly. Some claims are embellished, but core achievements are solid. Binomial theorem by early 1665. Method of fluxions developing through 1665 into 1666. Optical experiments spring 1666. Gravity calculations beginning 1666. The foundation is real. The timeline is documented. The work is extraordinary, even if not quite as miraculous as later stories suggest. Daily life at Woolsthorpe supports this intensity. Small house, quiet surroundings, few interruptions. His mother runs the farm with tenants. Newton has his room, his books, his equipment, his time. He establishes patterns that last lifetime, working through nights when ideas flow. Eating irregularly, forgetting sleep, forgetting meals, complete absorption in problems. The Bodkin experiment typifies his approach. Question arises: how does I create color perception? Design test? Perform test regardless of discomfort or risk. Document results. Draw conclusions. Move to next question. No hesitation, no fear, no limits except physical capability and available tools. He pushes both to extremes. Stays awake calculating until exhausted. Experiments on own body until limits reached. Tests, theories, until proven or disproven. Records everything meticulously for future reference. The intellectual transformation happening at Woolsthorpe extends beyond individual discoveries. Newton is creating new way of understanding nature, not appealing to authorities, not relying on ancient texts, not accepting received wisdom, observing directly, measuring precisely, calculating exactly, testing rigorously, proving mathematically. This is modern scientific method emerging. Galileo started it, Bacon described it, Descartes philosophized about it. Newton perfects it, makes it systematic, makes it mathematical, makes it powerful enough to unlock nature's deepest secrets. The Principia, 20 years later, will demonstrate the power fully, but the method forms here, in this room, at this desk, during these months, when young man with time and tools and questions figures out how to get answers that actually work, that actually predict, that actually explain. The records survive. We can trace his work. The Waste Book. Manuscript Ad 4004 at Cambridge University Library. Mathematical notebook from 1664 to 1666. Contains calculations on fluxions dated May 20th, 1665. The college notebook. Manuscript Ad 4000. More calculations, more dated entries. The October 1666 tract. Manuscript at 3958, 29 pages on fluxions, nearly 10,000 words, propositions, proofs, diagrams, all in his handwriting, all still readable, all evidence of what he actually did during isolation. He works in his bedroom upstairs. The window faces south. Good light for prism work. 22 feet to the far wall. He needs the distance for spectrum to spread. He makes notes on everything. Records, observations, draws diagrams. Numbers fill pages. Calculations stack. He tests ideas experimentally when possible, mathematically when not. He reads constantly. Descartes, Wallace, Oughtred, Viet, von Schutten's Latin translation of the Geometrie with commentary. He takes notes in margins, dog-ears pages, creates handwritten indexes, treats books as working tools, uses them to destruction. He buys equipment, prisms, multiple prisms for the two-prism experiment, lenses, chemicals, a furnace. He's doing alchemy work too, not just optics and mathematics. He's investigating material nature, trying to understand composition, transformation, properties of matter. The notebooks show chemical experiments, recipes, procedures, results. He's a vigorous experimenter, doesn't just theorize, tests, builds, measures, records. When he can't get answers experimentally, he calculates. When calculations fail, he invents new mathematics. When existing theories don't match observations, he develops new theories. Consider the experimentum crucis again. The crucial experiment. The setup reveals his method. First observation, spectrum is oblong, not circular. Classical theory says it should be circular. Something's wrong. Generate hypotheses. Maybe glass thickness matters. Test. Use different thicknesses. Result, still oblong. Hypothesis eliminated. Maybe angle of incidence matters. Test. Try different angles. Result, spectrum shape persists. Hypothesis eliminated. Maybe imperfections in glass. Test. Use different prisms. Result, same oblong spectrum. Hypothesis eliminated. Maybe the phenomenon itself reveals something fundamental. Design new test. Isolate one color using slit. Pass through second prism. Observe result. The color doesn't change. It just refracts at its characteristic angle. Conclusion. Colors are inherent in light. Prism separates, doesn't create. This is modern scientific method. Systematic hypothesis testing. Controlled experimentation. Clear observations. Logical deduction. It's 1666. Francis Bacon outlined the method earlier in the century. Galileo used experiments, but Newton takes it further, makes it rigorous, designs experiments to eliminate alternatives, creates apparatus specifically to test predictions. The experimentum crucis gets its name from this approach. Experimentum crucis means crucial experiment, the experiment that decides between competing theories, the crossroads experiment, the one that points the way. Bacon used the term instantiae crucis, instances of the finger post, the signpost at the crossroads showing which way to go. Newton's two-prism experiment is the signpost, shows definitively that light is composite. Not simple, not corrupted by glass, composite from the start. The same rigor applies to mathematics. The October Tract on fluxions doesn't just assert methods, it proves them. 7 propositions, each builds on previous, each demonstrated with geometric reasoning and algebraic manipulation. This is pure mathematics, no physics yet, just the tools, the methods for handling change, for computing rates, for finding areas under curves, for determining tangent lines, for solving differential equations before they're called differential equations. He's creating the machinery that will let him solve physics problems 20 years later. He doesn't publish any of this. Doesn't tell anyone except Isaac Barrow, his mathematics professor, who shows it to John Collins, another mathematician, in June 1669. Newton wants the methods to remain secret. He's 26, just appointed Lucasian professor, youngest ever. His reputation is building, but he's cautious, secretive, doesn't want credit stolen, doesn't want criticism, works in isolation even when he's back at Cambridge. The isolation at Woolsthorpe is different. This is forced, external. The plague makes the decision. Once it's over, Newton returns to Cambridge. April 1667. 6 months later, he's elected Minor Fellow of Trinity College. 2 years after that, Lucasian Professor of Mathematics, his life accelerates. But he later insists that those plague years were his peak creative period, prime of age for invention. Why? Freedom. No constraints, no obligations. Time to think deeply, to pursue questions without interruption, to develop ideas fully before presenting them, to make mistakes privately, to refine methods until they work, to build foundations without pressure to produce results immediately. Modern scholars debate how much Newton actually accomplished in 1666 versus how much he reconstructed in memory decades later. His own accounts, written in old age, sometimes conflict with dated manuscripts. He claims to have thought about gravity extending to Moon's orbit during plague years. Manuscripts show the gravity work developed mostly in 1670s and 80s, especially after correspondence with Robert Hooke in 1679 and 1680. He claims to have invented calculus completely during 1665 and 1666. Manuscripts show continued development through 1670s. Some dates on documents don't match his later recollections, but the core remains solid. The dated notebooks prove he was working on fluxions by May 1665. The October 1666 tract proves he had essential calculus methods by then. The prism experiments definitely happened at Woolsthorpe in spring 1666. He describes them in detail in his letter to Royal Society in February 1672. The optical work is documented. The mathematical work is documented. The astronomical thinking, connecting gravity to planetary motion, probably begins during plague years, even if full development comes later. The legend exaggerates, makes it too neat, too sudden, too miraculous. But the reality is extraordinary enough. A 23-year-old in rural Lincolnshire laying groundwork for 3 revolutions: calculus, optics, gravitation, all during forced isolation from plague. The Woolsthorpe environment matters. Small manor house, stone, medieval, his birthplace. His mother Hannah lives there with her second husband's property, now hers. Newton has his room upstairs. Privacy, quiet, the orchard with apple trees, the garden, rolling countryside. No noise, no crowds, no plague victims dying in streets like in London, no overwhelmed hospitals, no mass graves, just rural peace and space to think. The farm continues, work continues, life continues, but isolated from urban chaos, from academic politics, from social obligations. He can set his own schedule, work through the night if ideas flow, sleep late if exhausted from calculations, eat when hungry, walk in orchard when stuck, return to desk when solution appears. He never experiences conditions like this again. At Cambridge, there are lectures to give, students to advise, college politics, Royal Society correspondence, disputes with other natural philosophers, publications, criticism, defense of theories, experiments to replicate publicly, demonstrations. Later, there's the Mint, Parliament, Presidency of Royal Society, fame, recognition, obligations. The plague years at Woolsthorpe give him 2 years of pure intellectual freedom. No wonder he looks back on them as peak creativity. They probably were. Consider daily routine. We don't have detailed accounts from 1666, but we know his later habits. His assistant Humphrey Newton describes him in 1680, and never learned to go to bed at proper times once a problem seized him. Would work through nights, forget to eat, wake in yesterday's clothes. In winter, loved eating apples. Sometimes at night would eat a small roasted quince. Solitary, silent, thinking constantly, exercising his mind even during recreation. At Woolsthorpe during plague years, these tendencies are already forming. The intense focus, the ability to shut out everything except the problem at hand, to think on it continually, to keep subject constantly before him, to wait for first dawnings to open slowly into full clear light. The mathematical work requires this focus. Calculus problems don't solve themselves. You can't interrupt differentiation to chat about weather. The prism experiments require patience, careful measurement, multiple trials, systematic variation of conditions, detailed recording. The gravity calculations require astronomical data, geometric reasoning, algebraic manipulation, numerical computation, everything done by hand, no calculators, no computers, just paper, pen, and mind. Hours spent on single calculations, days spent on single problems, weeks spent on single theories, months spent developing methods. This is what genius looks like in practice. Not sudden illumination, sustained effort, deep focus, intellectual endurance. The Apple story captures imagination because it's simple. One moment, one object, one idea. Everything changes. That's how we want genius to work. Inspiration, revelation. The sudden flash, reality is messier. The apple is real. The observation is real. But it's embedded in months of prior thinking about circular motion, about Kepler's laws, about forces required for orbital mechanics. It's embedded in mathematical tools he's spent years developing. It's embedded in experimental methods he's honing with prisms. The apple doesn't create the insight. The apple focuses thinking that's already happening, gives concrete example, prompts specific question, suggests extension from terrestrial to celestial, from falling apple to orbiting moon, from local gravity to universal gravity. And even then, the full theory waits 20 years. The apple falls in 1666. The Principia publishes in 1687. 21 years. Most of the work happens in the 1680s after astronomer Edmund Halley visits Newton in Cambridge in August 1684 and asks whether inverse square force produces elliptical orbits. Newton answers immediately. It produces an ellipse. Halley is amazed, asks for the calculation. Newton looks for the paper, can't find it, promises to recalculate and send it. He does. 9 pages. De motu corporum in gyrum. On the motion of bodies in orbit, Halley receives it, realizes its importance, begs Newton to publish. Newton begins writing. 18 months later, the Principia exists. Halley pays for publication himself. Royal Society has no funds. The book appears July 1687. It changes everything, but the seeds were planted at Woolsthorpe, the methods learned, the questions asked, the connections glimpsed. Newton, at 23 in 1666, has the tools and intuitions. Newton, at 43 in 1686, has the proof and synthesis. The miracle year starts the process, doesn't complete it, gives the foundation. The structure builds over decades, with interruptions, with detours into optics and alchemy and theology, with disputes and distractions, but always returning, always building, always refining. Because once Newton asks a question, he doesn't let go. He thinks on it continually, waits for the answer to emerge, and eventually it does. The tree still stands at Woolsthorpe, the apple tree, flower of Kent variety, first mentioned in 15th century. The original blew down in storm in 1816. Locals propped it up. Another storm around 1820 knocked it down again. It rerooted, regrew from the base, still alive today, 350 years old. Grafted descendants grow at Cambridge, at MIT, at universities worldwide. Physical connection to the moment, to the legend, to the story we tell ourselves about genius and discovery and sudden insight. The tree represents something true and something false. True, Newton was at Woolsthorpe. True, he worked on gravitation theory. True, he saw apples fall. True, the observation prompted thinking about universal gravity. False, it happened in one moment. False, the theory emerged complete. False, one apple solved everything. False, genius works through sudden revelation rather than sustained effort. The manuscripts tell the real story, the dated entries, the crossed-out calculations, the marginal notes, the corrections, the progressive development visible on pages. This is how discovery actually works, not lightning bolt. Accumulated effort, layer upon layer, draft upon draft, test upon test, question upon question, connection upon connection, pattern upon pattern, until finally the structure stands complete, until finally the theory explains observations, until finally the mathematics produces correct predictions, until finally the experiments demonstrate the principles, until finally the work is ready to share, to publish, to defend, to add to human knowledge. Newton keeps most of this private for years, decades. He publishes the optical work in 1672, creates immediate controversy. Robert Hooke claims Newton is just elaborating on Hooke's earlier experiments, claims Newton's corpuscular theory of light is wrong, wave theory is correct. The dispute lasts years, makes Newton hate publication, hate criticism, hate exposure. He resolves to share nothing else unless forced. The calculus stays unpublished until 1693 for differentiation notation, 1737 for full method. By then, Gottfried Leibniz has independently developed calculus. Published first in 1684, bitter priority dispute erupts. Newton accuses Leibniz of plagiarism. Leibniz accuses Newton of hiding work then claiming priority. Both developed it independently. Modern consensus accepts this, but the dispute poisons Newton's later years, makes him vindictive, secretive, paranoid. The plague years show Newton before fame, before disputes, before the political battles and professional jealousies and priority fights, just a young mathematician with tools and questions and time. The isolation is forced, but welcome. The freedom is circumstantial, but productive. The conditions are temporary, but transformative. When plague ends and Cambridge reopens, Newton returns. But he carries notebooks full of discoveries, mind full of methods, vision full of connections. He's no longer a graduate student. He's one of the leading mathematicians in the world. Nobody knows it yet. He hasn't published, hasn't shared, hasn't demonstrated, but the work is done. The foundation is laid. The revolution is coming. It will take 20 years to emerge fully, 20 years to gather evidence, to refine theories, to write the Principia, but the core emerges at Woolsthorpe, in isolation, in 1666, in the rooms upstairs, in the orchard below, where apples fall and light refracts and mathematics flows and gravity extends from earth to moon to all the heavens. In October of 1666, Newton completes the tract on fluxions. 29 pages. The manuscript survives at Cambridge. The final sentences are calculations of motion, bodies revolving, circular paths, angular velocities, compound motions. The last proposition addresses forces, central forces, inverse forces, distance relationships. The mathematical tools are ready. The physical questions are forming. The next step is applying the tools to the forces, determining the orbits, proving the laws, but that will wait. For now. There's still plague, still isolation, still time to work, to calculate, to experiment, to think on it continually, to let first dawnings open slowly into full, clear light. By spring 1667, conditions improve. Plague recedes. University reopens. Newton packs notebooks, packs books, packs prisms and equipment, returns to Cambridge. Life resumes, different life. The questions from Woolsthorpe remain, the methods remain, the vision remains. But now there are lectures, obligations, students, the wider world. He's elected fellow, given rooms at Trinity, begins teaching. But in private, in his chamber, the work continues. The optical experiments grow more elaborate. The mathematical techniques grow more sophisticated. The astronomical calculations grow more precise. The foundation from plague years supports everything that follows. The tower rises on that base, the edifice of modern physics. The mathematical principles of natural philosophy, the theory that explains the cosmos, all beginning in a stone house in Lincolnshire, in a room with a drilled shutter, in an orchard where apples fall, where a young man sits and thinks and calculates and discovers that the universe operates by laws, mathematical laws, laws that can be known, laws that can be proven, laws that unify heaven and earth, all the work of those isolated months. Those productive years, that annus mirabilis that wasn't one miraculous year but 2 years of grinding, methodical, obsessive work. The Cambridge archives hold the proof. Manuscript ad 3958, the notebooks. The calculations dated May through November 1666. The tract from October, 29 pages, nearly 10,000 words, 7 propositions on fluxions. The foundation of calculus, manuscript, ad 4004. The waste book. More calculations, earlier dates, May 1665, November 1665. The progressive development visible, manuscript at 4000. The college notebook, additional work, additional dates. Additional evidence of what he actually accomplished versus what legend claims. The Newton Project makes it all available online, images of the manuscripts, transcriptions, normalized texts. Anyone can read what Newton wrote, can see his handwriting, his diagrams, his corrections, can trace the actual development of his ideas, can separate fact from legend, can understand that genius isn't magic and isn't sudden inspiration, is sustained effort, deep focus, methodical work, and sometimes circumstances that allow that work to flourish, like forced isolation, like a plague year, like 2 years at Woolsthorpe with nothing to do but think. In 1726, 60 years after the apple, Newton tells William Stuckley the story. They sit under apple trees, old man sharing memory with friend. Newton is 83. The story has grown, sharpened, been told many times, honed for effect. It illustrates the principle perfectly. Apple falls down toward Earth's center, moon orbits but doesn't fall away, same force, different magnitude, inverse square law, universal gravitation. The story works, becomes famous, gets embellished further by others. Apple hits his head, sudden revelation, complete theory instant. None of that is what Newton tells Stuckley. Newton says the fall of an apple occasioned thinking, prompted question, started chain of reasoning. That's accurate. That's how it worked. That the story serves the principle, makes it memorable, but obscures the process. The months of work, the failed calculations, the set-aside problems, the gradual development, the eventual return. The final solution, years later, Stuckley publishes the memoir in 1752, 26 years after Newton's death. The Apple story enters popular consciousness, gets repeated, gets modified, gets simplified, until we arrive at the version everyone knows. Newton sits under tree, apple falls, hits his head. He discovers gravity instantly, the version that makes no sense, because gravity was already known. Things fall. That's not news. The discovery is that terrestrial gravity and celestial mechanics are the same thing, that the force pulling apples also holds planets in orbits, that there's one universal law governing all motion and attraction everywhere in the universe. That's the insight. That's the revolution. And it takes months to formulate, years to prove, decades to publish. Not one afternoon, not one apple, one career, one life devoted to understanding nature through mathematics, the apple tree at Woolsthorpe stands as testament to the real story, to the actual work, to the man who sat in that orchard in 1666, with notebooks full of questions and methods full of power and mind full of curiosity, who watched apples fall and saw in that simple observation a connection spanning from Earth to Moon, who had mathematical tools to test the connection, who made the calculations, who found they answered pretty nearly, who knew he was onto something fundamental, who pursued it patiently over decades until the full theory emerged, until the Principia appeared, until the world understood what he discovered, that the universe is knowable, predictable, mathematical, governed by laws, and that human minds can discover those laws through reason and observation and calculation. That's what happened at Woolsthorpe. That's what the apple symbolizes. Not instant genius, not magic, but something more impressive. Human intelligence applied with discipline and patience and rigor over sustained time, creating knowledge, building understanding, changing everything.